In the warm shallows of northern Australia, danger does not always announce itself with a fin, a shadow, or a sudden burst of movement. Sometimes it drifts almost weightlessly through water so clear it seems empty. The sand below is pale and clean, the sunlight breaks into shifting silver patterns, and small fish move through the edges of mangrove creeks and coastal bays as if the whole world has been made harmless by beauty. This is exactly what makes the box jellyfish so disturbing. It belongs to an environment that looks open and safe, yet its body is built around one of the fastest biological trigger systems in the animal kingdom. It does not need to stalk anything. It does not need jaws, claws, muscle, or even a brain in the way most people imagine one. Its weapon is contact, and in the ocean, contact can happen before awareness. The box jellyfish seems too delicate to be a serious animal at first glance. Its bell is transparent, almost glass-like, with four corners that give it that strange, squared shape. From those corners trail long tentacles, thin as wet threads, nearly invisible in bright water. But those threads are not passive decoration. They are armed with countless microscopic capsules called nematocysts, each one functioning like a tiny pressure-loaded harpoon. When the right chemical and mechanical cues touch the tentacle, these cells can fire with astonishing speed, punching into skin and delivering venom before the victim has time to understand that the water has changed. It is not a bite. It is not a decision. It is a reflexive biological trap, repeated thousands of times along a line the eye can barely see. For small prey, this system makes brutal sense. A fish or shrimp brushing against the tentacles has only a fraction of a second to escape before the stinging cells anchor and venom begins disrupting its body. In a world where jellyfish have no gripping limbs and no hard mouth parts for chasing down fast prey, speed has to come from chemistry and engineering. The tentacles become a living net, and the venom becomes the force that prevents the prey from simply swimming away. The animal's body may look fragile, but its feeding strategy is ruthlessly efficient. It turns the surrounding water into a detection field. Anything small enough, unlucky enough, and close enough can become food without the jellyfish ever needing to lunge. That is the first uncomfortable truth about the box jellyfish. It is not evil or dramatic. It is highly specialized. Evolution did not build it to frighten swimmers. Evolution shaped it to catch prey in moving coastal water, where hesitation would mean starvation. The venom has to work fast because the prey is not trapped in a burrow or pinned under claws. It is surrounded by escape routes. A fish struck by a weak toxin could vanish in a flash, leaving the jellyfish with nothing but empty water. So the venom evolved for immediate impact, pain, paralysis, cardiovascular disruption, and systemic shock. In humans, that same speed becomes terrifying because the body is much larger, but the venom's message is still delivered with shocking force. The system was designed for prey control, yet accidental contact with a person reveals how powerful that design really is. In tropical Australian waters, the box jellyfish is also a reminder that visibility is not the same as safety. Humans are built to fear what we can see clearly: teeth, eyes, movement, size. The box jellyfish breaks that instinct. It can hang in the water like a piece of glass, its outline disappearing against sun glare and surface shimmer. Waves, bubbles, and suspended particles can hide the tentacles even more. A swimmer may see the beach, the sky, the bright shallows, and believe they have read the scene correctly. But the most important line in that scene may be invisible. One touch across the arm, leg, or torso can turn calm water into an emergency because the venom does not wait for panic to begin. It creates it. The pain is not just a warning signal, it is part of the body being overwhelmed. Severe stings can produce intense burning pain, skin welts, nausea, collapse, and dangerous effects on the heart and circulation. In water, this matters even more because a body in panic is a body losing control. Swimming requires rhythm, breathing, orientation, and decision-making. Venom attacks all of those indirectly by forcing the nervous system into alarm. The victim may not only be hurt, they may be suddenly disorganized inside an environment where disorganization can become fatal. This is why the box jellyfish feels like a biological emergency switch. It does not merely injure tissue at the point of contact, it can drag the whole body into crisis. Yet the animal itself is not helplessly drifting in the way many people imagine jellyfish drift. Box jellyfish are more active than the soft, aimless blobs people picture. They have complex visual structures called rhopalia, with multiple eyes that help them respond to light, obstacles, and habitat. That detail should stop the viewer cold, because it means this transparent creature is not just a floating bag of venom. It is sensing the world. It can navigate mangrove edges, avoid certain barriers, and move through its environment with more purpose than its ghostly body suggests. Its nervous system is simple compared with a fish or mammal, but simple does not mean primitive in a useless way. It means stripped down to what works. The coastal ecosystem around it is full of pressure. Small fish shelter near mangroves because roots create cover. Crustaceans hide in sediment and seagrass because open water is dangerous. Predators patrol the same nursery zones because young animals gather there. The box jellyfish fits into this system as a nearly invisible predator of the in-between spaces, drifting and swimming where light, tide, and prey movement overlap. It does not dominate the ocean by strength. It dominates a narrow ecological role through contact efficiency. In that sense, its body is almost the opposite of a shark or crocodile. Those animals make danger visible through mass and power. The box jellyfish makes danger vanish until the final moment. There is a cold irony in how beautiful its world can look. Northern Australia's tropical coast can appear peaceful enough to invite carelessness. Warm air, bright water, mangrove shadows, the smell of salt and mud, small fish flashing like scraps of metal beneath the surface. But beauty is not a safety certificate. Ecosystems are not designed around human comfort. They are built from hunger, defense, reproduction, competition, and survival. The same clear water that lets sunlight reach seagrass can hide a nearly transparent hunter. The same tidal creeks that protect juvenile fish can also concentrate the predators that feed on them. What looks like paradise from above can be a battlefield at skin level. The box jellyfish earns its place at the beginning of this venom protocol because it changes the rules immediately. It proves that an Australian strike does not need a chase scene. It does not need warning colors, a raised head, a hiss, a splash, or a visible attack posture. It can arrive as a line in the water, too thin to notice, carrying thousands of microscopic triggers ready to fire. The animal's power is not in aggression, it is in readiness. Every tentacle is a loaded border between the jellyfish and the rest of the sea. And that is what makes it such a perfect opening predator for this story. The box jellyfish is not a monster hiding in the deep. It is a transparent specialist moving through shallow, sunlit water, doing exactly what evolution shaped it to do. It catches prey by turning touch into chemistry and chemistry into collapse. For small animals, that means capture. For humans, it can mean sudden terror inside a place that looked harmless seconds earlier. In Australia, the first lesson of venom is simple and unforgiving. Sometimes the strike you never see is the one your body feels first. In the shallow rock pools and reef flats of Australia, the blue-ringed octopus lives in a world that changes by the hour. At high tide, water floods through cracks in the reef, lifting seaweed, pushing shrimp from their hiding places, and turning quiet stone basins into hunting corridors. At low tide, those same pools become isolated bowls of warm, oxygen-shifting water where every animal must calculate risk differently. Small crabs wedge themselves under rubble. Gobies hover close to the sand. Snails seal themselves against the drying air. And somewhere among the shells, algae, broken coral and shadowed crevices, an octopus no bigger than a human hand can become almost impossible to notice. Its body is soft, flexible, and visually obedient to the background, able to flatten, curl, darken, pale, and disappear into textures that would fool almost anything moving too quickly to inspect the details. That is what makes the blue-ringed octopus so unsettling. The famous rings are not always blazing like warning lights. Much of the time, the animal is subtle, mottled, and withdrawn, using camouflage before advertisement. Like many octopuses, it survives first by not being seen. Its skin can shift tone and pattern through specialized pigment cells, turning the body into a living surface that imitates rock, sand, shell grit, or algae shadow. This is not decoration. It is nervous system control written directly into the skin. A creature with no armor and no speed advantage over many fish has learned to make visibility optional. In the tide pool, where herons, fish, eels, and larger predators search for anything soft enough to swallow, invisibility is not a trick. It is shelter. But when concealment fails, the animal changes the message. The blue rings appear with a force that feels almost artificial, electric, circular, too vivid for such a small body. They are not there to charm anything. They are a warning display, a last bright sentence in a language predators are meant to understand. This is not worth touching. Blue-ringed octopuses are highly venomous cephalopods found in Indo-Pacific habitats including reefs, rocky seabeds, tide pools, seagrass, and algal beds. And the blue-lined species in Australia is specifically known for a paralyzing venom containing tetrodotoxin. The cruel joke is that humans often see the exact same signal as beauty first and danger second. That is a bad order in nature. Nature does not care whether a warning sign is attractive. The hunting method is quieter than the reputation. This is not a predator built for dramatic pursuit. It searches through tight spaces where a larger hunter cannot move with precision, slipping arms into crevices, feeling with suction cups, tasting surfaces, and reading the chemical leftovers of hidden prey. A crab beneath a stone may believe it has chosen the safer place, but the octopus is made for spaces like that. Its body can pour through a gap that seems too narrow for an animal with eyes and organs. Its arms explore separately, yet intelligently, each one loaded with sensory information. The octopus does not need to overpower a crab in open water. It can find the seam in the shelter, grip the shell, deliver venom with the beak, and turn the prey's defensive armor into a locked room. Tetrodotoxin gives this small predator an oversized biological authority. The toxin interferes with nerve signaling by blocking voltage-gated sodium channels, which are essential for electrical impulses in nerves and muscles. When those signals fail, Paralysis and respiratory failure can follow. In simple human terms, the brain may still be trying to command the body, but the message cannot travel properly. That is why this protocol feels different from the box jellyfish. The jellyfish is immediate shock, pain, and violent alarm. The blue-ringed octopus is the horror of silence. A bite can be small. The wound can look almost meaningless. The first mistake is believing that danger should look proportional to injury. For prey, this makes perfect evolutionary sense. A crab is not an easy meal. It has claws, a hard shell, leverage, and the stubborn personality of an animal that has spent its life being attacked from every direction. A weak predator gets pinched, injured, or exhausted. The blue-ringed octopus solves that problem with precision chemistry. Instead of fighting armor with armor, it attacks the nervous system behind the armor. Once movement fails, the shell no longer matters. The crab's defenses remain physically present, but the body inside can no longer use them properly. This is one of evolution's colder lessons. The strongest structure in the world becomes useless if the control system goes quiet. The octopus itself is not immune to the risks of its lifestyle. Tide pools are unstable homes. Sunlight can heat them, rain can dilute them. Oxygen can drop during calm, warm periods. Predators can trap animals in shrinking water until there is nowhere left to flee. For a soft-bodied cephalopod, the answer is behavioral flexibility. It hides by day, hunts carefully, and treats exposure as a cost. Many blue-ringed octopuses are more active at night, when shadows soften the reef and crustaceans begin moving under less visual pressure. In darkness, the octopus's body becomes even more suited to the job, arms reading the world through touch and taste, eyes tracking contrast and movement, skin changing tone as it crosses from sand to rubble to weed. Even reproduction carries a brutal edge. In blue-lined octopuses, recent research reported that males can use venom during mating, biting larger females near the aorta and temporarily paralyzing them, likely reducing the risk of being eaten during a dangerous encounter. That detail matters because it shows the venom is not just a weapon pointed outward at prey or accidental human victims. It is woven into the animal's whole survival strategy. Predation, defense, and reproduction all take place in a body small enough to fit in a palm, but dangerous enough to make size almost irrelevant. In this animal, evolution did not build a giant, it built leverage. The human fear around the blue-ringed octopus comes from that mismatch between beauty and consequence. A person sees a tiny animal in shallow water, maybe resting in a shell or moving delicately across a rock, and the mind files it under interesting, not catastrophic. That is where the danger begins. The animal is not aggressive in the cartoon sense. It does not want a battle with a creature hundreds of times heavier. But if handled, trapped, or pressed against skin, it has a bite capable of delivering a neurotoxic system completely out of scale with its size. The wound itself may not explain the danger. The nervous system explains it. This is why the blue-ringed octopus belongs as the second venom protocol. It teaches a different rule from the jellyfish. The first protocol was contact as crisis. The second is contact as shutdown. No roaring attack, no torn flesh, no theatrical violence. Just a small beak, a brief mistake, and a toxin that can separate intention from action. The victim may want to move. The muscles may still exist, healthy and intact. The lungs may still be structurally capable of breathing, but tetrodotoxin can interrupt the electrical language that makes all of that useful. In a world built on signals, blocking the signal is enough. And in the tide pool, the octopus returns to being almost invisible. The rings fade. The body settles back into the color of stone and weed. A crab shell lies open somewhere under the ledge. The water keeps moving as if nothing unusual happened. That is the deepest unease of this animal. It does not look like a weapon after the moment has passed. It looks delicate again, almost fragile, a small piece of living color folded into the reef. But Australia's coast has already taught the harder lesson. Some of its most dangerous animals do not need to look powerful. They only need one successful contact, one biological shortcut, and one body that underestimates what quiet venom can do. On the reef floor, the stonefish doesn't look like a predator waiting to happen. It looks like a mistake in the landscape, a lump of broken coral, a piece of algae-darkened rock, a sand-covered shape that the tide forgot to move. Around it, the shallow water keeps working. Sunlight fractures across the bottom, small fish flicker through coral rubble, shrimp pick at invisible scraps, and waves push fine sediment into every crack. Nothing about the scene tells the eye to stop. That is the genius of the stonefish. It survives by becoming part of the reef's visual noise, hiding not in darkness, but in plain sight, among textures too messy for the mind to separate quickly. In a place where bright colors often warn, attract, or advertise, the stonefish chooses the opposite strategy. It becomes forgettable. This is not laziness, it is precision. The stonefish's body is built for stillness, so complete that stillness becomes a weapon. Its rough, warty skin catches sand, algae, and small bits of debris, turning the fish into a living patch of seafloor. Its shape breaks the clean outline that would give most animals away. Predators search for movement, contrast, symmetry, eyes, fins, and clean body edges. The stonefish hides those clues under ugliness so effective it becomes beautiful in a very harsh way. It is one of those animals evolution designed without caring whether anyone would admire it. The result is not elegant like a shark or colorful like a reef fish. It is functional, and functional is often more frightening. Unlike the box jellyfish or the blue-ringed octopus, the stonefish does not depend on delicate contact in open water or a small bite delivered at close range. Its venom system is built into the architecture of being stepped on. Along its back are strong dorsal spines connected to venom glands. When pressure comes down from above, those spines can act like biological needles, driving venom into whatever made the mistake. That detail matters because the stonefish does not need to chase, aim, or decide. The reef itself supplies the trap. A foot, flipper, paw, or careless predator presses down, and the hidden animal answers through pressure. The contact is accidental from the victim's side, but from the stonefish's design, it is perfectly prepared. This is the third venom protocol: pain as instant control. The stonefish is famous for producing extreme pain, and that pain is not just a dramatic detail for human fear. Pain changes behavior. It breaks focus. It forces muscles to withdraw, balance to fail, breathing to sharpen, and decision-making to collapse into panic. In shallow water, that becomes especially dangerous. A person who can stand safely 1 second can become disoriented the next. A reef that looked calm can suddenly become an unstable surface of sharp coral, moving water, and nowhere comfortable to place weight. Pain does not only hurt the body, it reorganizes the entire situation around survival. The stonefish does not need to win a fight. It makes the fight impossible to continue. For the fish itself, this venom is primarily defensive, and that is where the stonefish becomes more interesting than a simple, dangerous animal label. It is not sitting on the bottom hoping to sting swimmers. It is trying to avoid being eaten. A slow, bottom-dwelling fish with poor escape speed needs a different answer to predators. Camouflage handles the first part. Do not be noticed. Venom handles the second. If noticed and attacked, become too costly to touch. Many animals survive by running, schooling, armoring themselves, or showing warning colors. The stonefish combines disappearance with punishment. It does not advertise danger from a distance. It lets the attacker discover the truth at the worst possible range. But the stonefish is not only a hidden landmine, it is also a predator, and its feeding style is as sudden as its defense is passive. Small fish and crustaceans moving near the bottom may pass within reach of what looks like nothing. Then the mouth opens with explosive speed, creating suction that pulls prey inward before the prey has time to correct its path. This is ambush predation stripped down to timing. The stonefish saves energy by waiting, using the reef's clutter as cover, then turning a tiny distance into a fatal one. In reef ecosystems, where every calorie costs risk and effort, this matters. A predator that can remain still, blend in, and strike only when success is likely does not waste much. It lets the habitat do half the hunting. The reef floor is full of animals playing versions of this same game. Crabs freeze against rock. Flatfish bury into sand. Octopuses change skin texture and color. Scorpionfish imitate coral and weed. The stonefish belongs to this world of visual deception, but it pushes the strategy to a more severe conclusion. It is not merely hiding from prey, it is hiding from nearly everyone. Its camouflage works downward against hunting fish, sideways against passing crustaceans, and upward against anything moving over the bottom. The animal becomes a blind spot in the ecosystem, a place where the landscape has secretly grown venomous spines. There is something especially cruel about the fact that the strike often begins with confidence. A shallow reef, a sandy lagoon edge, a tidal flat, or a rocky pool can feel readable to human eyes. The water may be clear enough to see shells and coral fragments. The bottom may look close enough to trust. But stonefish camouflage is designed to defeat exactly that kind of quick judgment. The animal does not need to be invisible in a magical sense. It only needs to be misidentified as part of the background. That is the important difference. Most victims do not fail because they see nothing. They fail because they see the wrong thing. Rock, sand, rubble, safety. For wild animals, this mistake can be just as costly. A predator nosing through the bottom for prey may strike at the wrong shape. A larger fish or ray investigating the reef floor can put pressure where it should not. The stonefish's spines are not built for show. They turn the predator's own force against it. The harder the pressure, the more serious the delivery can become. That is a brutally efficient defensive principle. Instead of spending energy attacking, the stonefish lets the attacker provide the energy required to activate the weapon. In mechanical terms, it is almost unfair. In evolutionary terms, it is perfect. The venom's effect adds another layer to the strategy. Extreme pain is already enough to force withdrawal, but severe stings can also bring swelling, tissue damage, weakness, shock, and wider systemic distress. The body reacts as if the entire nervous system has been pulled into an emergency. In water, the consequences are magnified because the victim still has to manage breathing, balance, and escape from the environment itself. A painful sting on land is one crisis. A painful sting in a moving marine landscape is two crises at once: the body's internal alarm and the external problem of getting out safely. That is why the stonefish earns its reputation so strongly. Its venom does not need to kill in order to dominate the moment. It only needs to make every next action harder. Even its ugliness has ecological intelligence. The bumps, folds, and rough skin are not random deformities, they are visual tools. Reef floors are not smooth backgrounds. They are chaotic mosaics of dead coral, living algae, shell fragments, sand ripples, sponge growth, and shadow. A cleanly shaped animal would stand out. The stonefish looks broken because broken things belong there. Its body tells predators and prey the same lie from opposite directions. Ignore me. To prey, that lie opens a feeding opportunity. To predators, it avoids attention. To anything unlucky enough to step down, it becomes a trapdoor. This makes the stonefish one of Australia's most unforgiving lessons in camouflage. It does not prove that the most dangerous animal is always the fastest or strongest. It proves that danger can be built into stillness. A shark must move through the water and declare itself eventually. A snake must lift, strike, or slip away. A crocodile may disappear at the surface, but when it attacks, the violence is obvious. The stonefish is different. Its most important action may be doing nothing at all. It waits until the world makes the mistake for it, and when that mistake happens, the reef changes instantly. The patch of bottom that looked dead becomes alive. The harmless rock reveals spines. The calm water becomes a place of shock, pain, and desperate movement. The stonefish remains where it was, not triumphant, not dramatic, just defended. That is what makes this protocol so brutal. The animal does not chase suffering, it simply makes contact expensive beyond belief. In Australia's shallow marine world, the stonefish survives by mastering the ugliest kind of camouflage, not hiding from danger, but making danger step on it first. In the blue-green water above an Australian reef, a sea snake can seem almost too calm to belong in a venom story. It does not burst from cover like a fish. It does not strike with the blunt violence of a crocodile or wait like a stonefish under a layer of sand. It moves with slow, controlled confidence, the body folding through the water in smooth waves, the paddle-shaped tail steering each turn with an ease that makes the whole animal look more graceful than dangerous. Sunlight breaks over the coral heads. Small damselfish flash electric blue near branching coral. Parrotfish scrape at the reef with beaked mouths, leaving faint trails of pale dust behind them. And through that bright, busy scene comes a reptile that looks strangely peaceful, as if it has forgotten the old panic of land and learned the ocean's rhythm instead. That elegance is exactly what makes it deceptive. A sea snake is not a relaxed ocean decoration. It is a highly modified descendant of land snakes, shaped by evolution into a hunter that can move through reef channels, seagrass beds, mangrove edges, and open coastal water with a body built for swimming. The tail has become flattened like an oar. The nostrils sit high and can close when the animal dives. The lungs stretch far down the body, helping with buoyancy as well as breathing. Some gas exchange can even happen through the skin, allowing certain species to stay submerged longer than a land snake ever could. But it is still a reptile. It still has to surface. Every dive is a negotiation between hunger, oxygen, temperature, and risk. The reef does not slow down for that negotiation. Prey disappears quickly here. Small fish vanish into coral branches. Eels slide into cracks. Gobies drop into burrows. A predator that hesitates loses the meal. That is why sea snake venom has to be efficient. In water, Injured prey cannot be allowed to swim far into a maze of coral or disappear into a hole too narrow to follow. A bite must begin the ending fast, even if the ending is not visible yet. Many sea snakes carry venoms with powerful neurotoxic and myotoxic effects, meaning the toxin can interfere with nerve signaling and damage muscle tissue. That combination is coldly practical in the ocean. Stop movement. Break strength. Prevent escape. Let the reef's complexity work for the hunter instead of the prey. A hunting sea snake may investigate the reef with patient, almost delicate precision. Its tongue flicks underwater, gathering chemical traces. Its head moves into crevices where small fish shelter. The body remains controlled, not frantic, because this is not a chase across open sand. It is a search through architecture. Coral reefs are cities of hiding places, tunnels, ledges, rubble slopes, sponge-covered gaps, and living branches that protect small animals from larger mouths. The sea snake enters that world like a specialist tool. It can probe where bulkier predators cannot fit. It can follow scent along invisible trails. It can turn its narrow head into the first part of the weapon, then deliver venom into a prey animal that thought stone and coral had made it safe. This is the fourth Venom Protocol, and it is more sinister because it does not always announce itself properly. The box jellyfish is immediate crisis. The stonefish is pain so violent it takes over the whole moment. The blue-ringed octopus is quiet shutdown. The sea snake brings something even more psychologically cruel: delayed betrayal. A bite may be small. The first sensation may not match the danger. There may be little tearing, little blood, and not enough drama to convince the mind that a serious event has begun. The ocean stays beautiful. The reef keeps glowing. The snake may already be gone, folding itself back into coral shadow. For a short time, the body can seem stable, and that false stability is the trap. Underneath, the chemistry may already be working. Neurotoxins can interfere with the signals that allow nerves to command muscles, while myotoxins can begin damaging muscle tissue itself. Weakness, stiffness, paralysis risk, and internal injury can develop with time, which makes the danger feel almost unfair. A person expects venom to behave like fire: immediate, obvious, impossible to ignore. Sea snake venom can behave more like a slow electrical failure inside a sealed machine. The outside may still look intact, the mind may still be clear, the water may still feel warm against the skin. But the body's ability to move, breathe, and remain chemically balanced can begin slipping away from underneath. For prey, that delayed collapse is not a flaw. It is a strategy that works inside a reef. A bitten fish may still twitch or push into cover, but the venom changes the direction of the struggle. Each second after the bite belongs more to the snake. A fish that once had speed now has failing coordination. A hidden eel that once had muscle now has less control inside its own shelter. In the narrow logic of predation, this is elegant. The sea snake does not need to crush or tear. It only needs to make the prey's body stop being a useful escape machine. The snake itself lives with limitations that make this design even more impressive. It cannot chew like a mammal. It cannot hold prey with claws. It cannot breathe water. Its body temperature depends on the surrounding environment, so tropical shallows and warm currents matter to its activity. In cooler conditions, movement and digestion can slow, and the animal must balance energy carefully. The ocean gives it access to prey, but also exposes it to larger fish, sharks, birds, and the constant physical pressure of waves and currents. Venom helps solve several problems at once. It reduces struggle, saves energy, and allows a relatively slender reptile to hunt animals that might otherwise be too quick or too difficult to subdue. There is another strange truth here. Sea snakes are often less interested in humans than humans are in them. Many encounters happen because people enter the same shallow marine spaces where the snakes hunt, rest, or surface to breathe. Divers may see one moving through coral and mistake calmness for harmlessness. Fishermen may pull one up in nets or traps. A swimmer may meet one at close range and misread curiosity, poor visibility, or breeding season movement as aggression. The snake's smooth motion works against it in human imagination. It does not look panicked, so it looks safe. That is a stupid assumption, and nature punishes stupid assumptions without making a speech. Even when the animal is not trying to attack, the weapon is still real. That is the hard lesson of venomous wildlife. Intent does not matter as much as contact. A sea snake does not need hatred, anger, or dramatic aggression to become dangerous. It only needs a defensive bite that delivers enough venom into the wrong body. The ocean does not pause afterward to explain the seriousness of what happened. The surface still shines, the reef fish still feed. The snake still needs to breathe, hunt, and avoid becoming prey itself. The victim is the one left discovering that a small wound can carry a long consequence. Cinematically, the sea snake is frightening because it refuses to behave like a monster. It is beautiful in a clean, controlled way. The scales catch sunlight as it turns. The body moves with the same economy as drifting weed, but with intention underneath. It surfaces quietly, breaks the water with a small breath, then returns below as if slipping between two worlds. It is both land animal and ocean hunter, ancient serpent and marine specialist. That dual identity gives it a strange authority. It carries the old venom logic of snakes into a place where escape is three-dimensional and prey can vanish into blue space. By the end of this chapter, the reef should not feel less beautiful. It should feel more honest. The beauty was never fake. It was just incomplete. The coral is still alive with color. The water is still clear, the snake is still graceful, but now that grace has a colder meaning. It is not softness, it is efficiency. The sea snake shows that Australia's venom protocol does not always explode at the point of contact. Sometimes it waits. Sometimes the strike is small, the pain is unimpressive, and the danger grows in the quiet space after everyone thinks the worst moment has already passed. That is delayed betrayal. The ocean remains calm while the body begins learning the truth. The platypus enters this venom story from a completely different doorway. There is no reef glare, no transparent tentacle, no hidden spine waiting under a careless foot. Instead, there is a shaded Australian creek at first light, where mist hangs low over the water and the banks are stitched together with roots, reeds, fallen bark, and damp soil. The surface looks quiet until a small ripple cuts across it. Then a strange shape appears, low, dark, and smooth, with a broad tail behind it and a bill that looks almost borrowed from another animal. The platypus does not arrive like a threat. It arrives like a biological puzzle, as if evolution assembled it after reading several instruction manuals at once and refusing to choose one. It is a mammal that lays eggs, a furred swimmer with webbed feet, a river hunter with no teeth as an adult, and a creature so odd that its danger feels almost like an afterthought, until the hidden spur becomes part of the story. The first thing to understand is that the platypus is not built around looking dangerous. Its body is shaped for freshwater secrecy. Dense waterproof fur traps a layer of air close to the skin, helping it stay warm in cold streams where a smaller animal would lose heat quickly. Its flattened tail stores fat and helps stabilize the body while swimming. Its front feet are broad and webbed, pushing water with strong, efficient strokes, while the back feet help steer. On land, it can look awkward, almost soft and clumsy, but underwater it becomes something else entirely, controlled, low, and purposeful. It dives beneath logs, slips through submerged roots, and searches the creek bed with the steady patience of an animal that knows most of its meals are hidden in mud. The bill is the real center of its world. It is not just a cute feature, and treating it that way is the kind of shallow thinking that makes wildlife content feel weak. The platypus hunts with its eyes, ears, and nostrils closed underwater, relying heavily on touch and electroreception. Tiny sensory receptors in the bill can detect faint electrical signals produced by the muscle movements of small prey. In a cloudy creek where visibility may be poor and the bottom is full of silt, that ability is almost unfair. A shrimp flicks, a worm contracts, an insect larva moves under gravel. The platypus does not need to see it clearly. The bill reads the hidden life of the river like a map written in pressure and electricity. This makes the platypus a serious predator, just not the kind people expect. It is not dramatic. It does not rip through prey with teeth or chase fish in open water. It works the bottom, scooping through sediment, finding larvae, freshwater shrimp, worms, and small aquatic invertebrates, then storing food in cheek pouches before surfacing to grind it down with rough pads inside the mouth. That detail alone should change how viewers see it. The platypus is not a floating toy. It is a specialized freshwater hunter tuned to a dark sensory world beneath the surface. Its whole body is an answer to the question of how a mammal can make a living in cold creeks, muddy banks, and low-visibility water. And then comes the venom, which feels almost impossible because it does not match the animal's public image. Male platypuses carry sharp spurs on their hind legs connected to venom glands. These spurs are not used to capture prey. That is the key point. This is not snake venom evolved for killing food, not jellyfish venom built for instant prey capture, and not stonefish venom waiting to punish an attacker from above. Platypus venom belongs to a stranger category, a mammalian weapon tied strongly to rivalry, defense, and breeding season conflict. During the breeding season, the venom glands become more active, and the spur becomes a serious tool in male competition. In other words, this is not a hunting system. It is a seasonal weapon in a private war most people never see. That makes the Platypus protocol different from every animal before it. The danger is not advertised through fangs, bright warning colors, or a threatening posture. It is hidden in the back leg, where almost nobody would look for venom. A predator grabbing a platypus, a person handling one carelessly, or another male locked in conflict can suddenly meet a weapon that feels completely out of place on a furred, duck-billed mammal. The spur can drive venom into tissue, and the result is known for severe pain and swelling. The pain can be intense and prolonged, which is exactly why this weapon makes sense in competition. It does not need to kill. It needs to punish, repel, and dominate close contact. In the breeding season, the calm creek becomes less peaceful than it looks. Male platypuses may overlap along stretches of river and compete for access to females, and that competition is not just symbolic. Beneath the surface and along the banks, territories, movement patterns, and encounters matter. A male with an effective venomous spur has a biological argument attached to his hind leg. That is darkly funny, but only because the animal looks so unlikely. If the same weapon belonged to a lizard or a snake, nobody would be surprised. Put it on a platypus, and suddenly the viewer has to rethink what venom even means. Australia did not simply place venom in obvious nightmares. It placed it in a mammal that already breaks half the rules people use to understand mammals. The ecology around the platypus makes that hidden weapon even more interesting. Freshwater environments are not gentle places. Creeks rise and fall with rain. Floods can reshape banks, tear out vegetation, and bury feeding grounds under silt. Drought can shrink habitat into isolated pools. Water temperature affects activity, prey availability, and the energy cost of foraging. A platypus may spend hours each night feeding because small invertebrates do not provide huge meals one at a time. It must dive again and again, surface to chew, dive again and keep working while avoiding predators such as foxes, dogs, large birds of prey, snakes, and goannas near the banks. Its life is not cute. It is demanding, repetitive, and finely balanced. Thermoregulation is part of that balance. A small mammal in cold water loses heat fast, and the platypus solves this with dense fur, a compact body, and behavior shaped around energy conservation. Every dive has a cost, every meal has a value, every burrow matters. Females dig nesting burrows into the bank, lay eggs, and nurse their young in one of the strangest reproductive systems among living mammals. They do not have nipples. Milk is secreted through the skin and collected by the young from the fur. It sounds almost invented, but it is real, and it shows how old and unusual this branch of mammalian evolution is. The platypus is not a failed version of a modern mammal. It is a survivor from a deeply ancient line carrying solutions that most mammals never used. That is why its venom feels so important in this chapter. It is not just a weird trivia point. It reveals that venom has evolved in places most people would never expect, for reasons beyond hunting. Venom can capture prey, defend against predators, settle competition, or raise the cost of physical contact. In the platypus, it becomes part of reproductive pressure. The animal's body tells a story about survival at multiple levels: sensory hunting through the bill, insulation through the fur, underwater movement through the feet and tail, reproduction through egg-laying, and conflict through the spur. Nothing about it is random, even if the final design looks absurd at first glance. A platypus moving through a creek at dawn does not look like a venomous animal. It looks quiet, focused, almost harmless. It surfaces with a soft ripple, floats for a moment, then folds back under the water and disappears beneath reflections of eucalyptus branches. That softness is the trap in how humans read it. We confuse familiar mammal features with safety. We see fur and assume gentleness. We see small size and assume weakness. But nature does not build animals for human categories. The platypus is not trying to fit our idea of dangerous or harmless. It is simply doing what its lineage has done for millions of years: hunting in dark water, breeding in riverbanks, surviving floods, avoiding predators, and carrying a hidden weapon for moments when close contact becomes unavoidable. So the fifth protocol is pain without the usual warning signs: no glowing rings, no raised fangs, no obvious stinger. Just a spur tucked away on an animal that already seems impossible before venom even enters the conversation. The platypus proves that Australia's venom story is not only about killers and ocean hazards, it is also about evolutionary surprise. A quiet mammal in a shaded creek can carry a chemical weapon built not for spectacle, but for pressure, rivalry, and defense. And that is what makes it unforgettable. The danger is not where the viewer expects it, because the animal itself is not what the viewer expects at all. The BullAnt brings the story back to dry ground, where danger is smaller, faster, and easier to insult by accident. After the ocean's invisible tentacles, silent neurotoxins, hidden reef spines, and venom tucked into one of the strangest mammals on Earth, the Australian bush seems almost honest again. Red dirt warms under the sun, dry grass rattles against itself in the wind. Eucalyptus leaves hang pale and leathery above the track, giving off that sharp, resinous smell that makes the whole landscape feel sun-baked and alive. At ground level, however, the country is not quiet. It is crossed by trails, chemical messages, buried chambers, and tiny territories defended with a seriousness that would be almost funny if the defenders were not armed. Somewhere beside a log, under a stone, or in the open soil, a BullAnt stands near its nest entrance, with jaws open, head raised, and eyes locked onto movement. This is not the soft, anonymous kind of ant people barely notice moving in a line across a kitchen wall. BullAnts feel different because they behave as if they know exactly where they are and exactly what has entered their space. Many ants live mostly through smell, reading the world through chemical trails and pheromone signals. BullAnts use chemistry too, but their eyesight gives them a more direct and unsettling presence. They can track movement with surprising confidence, turning toward a threat instead of simply scattering. From a human height, that may seem like a tiny detail. From ground level, it changes everything. The ant is not just a speck of irritation. It is watching, measuring distance, and deciding whether the moving shape above it has crossed the line from background to problem. Their eyes are part of why they seem so primitive and so advanced at the same time. BullAnts belong to an ancient and distinctive branch of ant evolution, and their long legs, powerful mandibles, and large eyes give them a hunting style that feels less like a blind swarm and more like individual patrol. They move over open ground with a kind of jerky confidence, stopping, turning, and accelerating when the world gives them a reason. They are predators as well as defenders, taking insects and other small arthropods that move through their territory. A grasshopper nymph, beetle, caterpillar, or stray spider crossing near the nest may find that the dry ground is not empty at all. It is being monitored by workers that can bite, grip, and sting with a persistence completely out of scale with their size. The sting is the center of this final protocol, but it should not be misunderstood as a tiny version of a snake bite. The BullAnt is not trying to bring down large animals as prey. It is not designed to kill a kangaroo, a dog, or a human walking past the nest. Its venom works as a command system. Pain is the message, and the message is simple: leave. That is what makes it so effective. A large animal does not need to die for the colony to win. It only needs to step away, drop the threat, stop digging, stop crushing the nest entrance, or stop standing in the wrong patch of dirt. In the logic of a colony, forcing retreat is victory. The sting is not there for drama. It is there because hesitation can destroy a nest. A BullAnt colony is more than a hole in the ground. Beneath the surface is a living structure with chambers, larvae, pupae, workers, and a queen whose survival shapes the future of the whole system. The surface entrance may look small, but it connects to an underground investment of energy and time. Workers forage outside, bring back food, defend the opening, and respond to disturbance with an intensity that makes sense once the nest is seen as a body rather than a place. The individual ant may be small, but the colony is the organism in practical terms. Each sting is a cell of that larger body firing back. That is why bull ants can feel so aggressive. Aggression is not personality here, it is ecology. An ant that waits too long near an exposed nest loses brood, food stores, or workers. Birds may scratch at the soil. Echidnas and other insect-eating animals may investigate. Reptiles, spiders, rival ants, and larger insects move through the same ground. Heat, drought, and sudden rain already make life difficult enough. A colony cannot afford to politely observe every large shadow that stops above it. So the workers respond fast. They move toward disturbance. They bite to anchor themselves. Then the sting follows, driving venom into the skin and turning a tiny contact point into an event the nervous system cannot ignore. Pain is often treated like a simple sensation, but in nature it is a behavioral weapon. It edits decisions. It breaks concentration. It forces the body to prioritize escape over curiosity. One bull ant sting can change the entire posture of a larger animal. A confident footstep becomes a flinch. A hand reaching toward a log pulls away. A predator nosing at the nest may jerk back and rethink the cost of the meal. That is the one-hit principle in its land-based form. Not every venom has to paralyze breathing or damage organs to matter. Sometimes the strongest outcome is immediate behavioral control. The animal that was advancing is now retreating. The threat that was calm is now distracted. The colony has bought space. There is also something brutally honest about the bull ant compared with the hidden weapons before it. The stonefish survives by being mistaken for nothing. The platypus hides venom in a place no one expects. The SeaSnake may leave a bite that seems too small at first. A bull ant, by contrast, often gives warning through posture and movement, but people miss it because they are too large to respect the scale. That is the mistake. Humans assume small animals occupy a small importance. The bush disagrees. At ant level, a fallen branch is a highway, a footprint is a landslide, and a nest entrance is a fortress gate. The bull ant is not overreacting. It is reacting to the world at its own scale, where a careless second can collapse a tunnel or crush a generation of young. The Australian environment sharpens this behavior. Dry heat can make open ground a dangerous place to forage, so timing matters. Shade, soil temperature, humidity, and the movement of prey all shape when workers are active. Insects are cold-blooded, and their muscles, speed, and responsiveness depend heavily on warmth. Too cold, and movement slows. Too hot, and water loss becomes a problem. The bull ant's day is not random wandering. It is a balance between opportunity and exposure. When conditions are right, workers range through leaf litter, grasses, and bare soil with the sharp alertness of animals that must find food while avoiding becoming food themselves. Their role in the ecosystem is not just to sting anything foolish enough to bother them. They are hunters, scavengers, soil movers, and prey for other animals. They help recycle nutrients by carrying dead insects and organic matter. They influence the tiny architecture of the ground around their nests. They become part of the food web for specialized predators that have learned how to handle ants or raid their colonies. Even their aggression has a place. A strongly defended nest can shape how other small animals move through the area, creating invisible borders in the landscape. The bush is full of these hidden maps, scent trails, hunting routes, thermal zones, territories, and danger patches that humans only notice when pain translates them into something obvious. What makes the bull ant a strong final chapter is that it strips venom down to its most practical meaning. Venom is not one thing. That weak idea needs to die. Venom is not always a killing fluid. Not always a predator's tool, not always a horror show of paralysis and collapse. It can be a net, a shutdown switch, a hidden spine, a delayed failure, a breeding season weapon, or a territorial command. The BullAnt finishes the sequence by showing venom as communication through pain. It tells the world where the colony begins. It tells predators that the meal is not free. It tells a giant foot that the ground under it is already occupied. At the end of the episode, the camera can stay low over the Australian dirt. Not in the ocean, not in a rainforest, not in some dramatic dark cave, but beside an ordinary nest on an ordinary patch of ground. A worker stands in the sunlight with its body lifted and mandibles open, the whole animal no longer than a fingernail, yet completely unwilling to behave like it is small. Around it, the dry grass moves, the heat rises, and the hidden colony continues beneath the soil. This is Australia's final lesson in Venom Protocol. Danger is not defined by size, beauty, or cinematic violence. Sometimes it is a tiny animal with good eyes, a loaded sting, and absolutely no interest in letting the giants pass without permission.